I can now calculate the r vector, the radius vector. I'm going to go ahead and pick the pivot point as my origin of coordinates, as my axis of rotation here. And I can quickly see that here's Rn, the radius for the normal force, here's an R2, and here's an R1, right? So those are the radius vectors. I already know how big each of these forces is. So given that, I am going to go ahead and write down some. One stands out right away. The torque by the normal force is 0. All right, I'm doing R cross F. The normal force is not 0, but the R is. So I'm going to get no torque by the normal force. That's cool. That's valuable, right? All right, let's move on. Torque 1, the torque by force 1, is going to be positive R1 times M1 times. And the way that I get that is I'm going to do this cross product, right? And there's two important features of the cross product. One is I need to get the magnitude. And the magnitude of the cross product is always going to be the magnitude of the first vector, which is R1, times the magnitude of the second vector, which is M1 times G, times the sine of the angle in between the vectors, which I ought to draw the vectors tail to tail. So maybe I'll draw them over here. So there's my force vector. Here's my radius vector. I've just translated those over into space. And the angle between those two vectors, sure enough, is 90 degrees. And the sine of 90 degrees is 1. So I don't end up with an extra factor from it. The last thing to note is that I'm going to need to find the direction of this torque. Torque is a vector, so I ought to find its direction. I can use the cross product for that. To do that, I can use the right-hand rule. My thumb is the first vector, R, points to the left. My first finger is the force vector, which points downwards. So my remaining fingers point out of the screen at me, which is a positive or counterclockwise torque. So that's why I've got the positive sign. I'll go through the last one a little more quickly. So the torque from force 2 is going to be negative. Again, you can do a quick right-hand rule and get that the torque here points into the board, which is negative. And then is again R2, the magnitude of the R vector, times F2, the magnitude of the F vector, times the sine of the angle between them. Again, this one's friendly, 90 degrees. Sine of 90 is 1, so I get negative R2M. Now I know all the individual torques. I can go ahead and add them up to get the net torque on the system, which I have collected here by factoring out B. I also know from Newton's second law of rotation that this ought to be equal to the moment of inertia for this board, which I don't know yet, but I could look up if I wanted to, times the angular acceleration alpha. And I don't have them on my slides here, but all of these are technically vectors, right? So these ought to be vectors. Now that I've got that, I can check in with my expectation, which was, I wanted to have alpha, the angular acceleration, be negative, point into the board so that the whole thing is going to rotate clockwise and launch the rock into the air, which means looking here that I actually need this whole expression to be negative. So if I kind of quickly set that up, that means I need R2M2 to be greater than R1M1. So that is my condition for this to work as a real useful catapult. And you'll notice that this expression is a little more complicated than any of the answer choices, right? It's not enough to say, oh yeah, M2 had better be bigger than M1. It's only that M2R2 had better be bigger than M1R.